We're now going to start the core part of the course, the study of three-dimensional graphics by looking at transformations, viewing, lighting and materials, texture mapping, and other discrete methods. So we're assuming now at this point we can program some basic WebGL applications, and now we can start with our discussion of geometry. And geometry is really the basis of almost everything we're going to do, and really the basic background for this goes back to what you probably studied in high school, although we might be taking a slightly different perspective. What we want to do is look at what's the minimum amount that we need to describe geometric ideas, and we'll see that there are three entities that are involved: scalars like the real numbers, vectors, and points, and we want to develop this in a very coordinate-free manner. Now this, depending on when you went to high school, may be very different from how you studied it, because one of the things when let's say the older form of studying geometry was to study Euclidean geometry, and you studied various theorems, and you started with some basic axioms, and you proved when two triangles were congruent. And if you think about it, that there was no notion of coordinate systems when you did that. But what happened, usually if you started that way, then you studied coordinate geometry later, where you assigned numbers to locations in the plane. But I think there's been a tendency to go away from the way that we used to study geometry and to start with coordinate systems. And what we'll find, if you really want to understand computer graphics, it's very dangerous to do that. So what we're going to do in this lecture is see how we can get, how far we can get without using any kind of coordinate system. And this is the notion of coordinate-free geometry. So we'll start with our basic entities and see that we need scalars, we need points, and we need vectors, and with them we can build the basic primitives that we need to develop computer graphics, and they'll be primarily line segments and polygons and principally triangles. So let's go and look at the basic entities. And geometry, if you want a definition of it, it's the relationship among objects in space, and we can do it in any number of dimensions, even though we'll wind up worried more about real-world problems, so that we'll be working in 3 dimensions. You'll see that almost all of the notions we'll talk about today are valid in any number of dimensions. And we want to be as simple as possible, so we'll talk about as simple a set of primitives as we need. Okay, so the notion of coordinate-free geometry is in contrast to this Cartesian approach. So if you took the Cartesian approach, then you said, well, a point is a location in space, and it has coordinates x, y, and z. What we want to do is say, no, a point is just a location in space, and I don't want to use a representation, and the key word is representation, at some location x, y, and z, because then you could say, well, what system are x, y, and z in? And I'd rather start with the coordinate-free notion and then get to representation in the next lecture. And what it does is, when you started in coordinate Cartesian spaces to study geometry, then everything was derived by algebra, because you could do very algebraic manipulations on the representation. And that's what I'm claiming is a little bit dangerous, and we'll see why. One reason I think behind this, and I probably should point this out, is that if you take a physical point of view, what a physicist might say, that look, these points exist in space. If I take a triangle, say, and it exists in space, regardless of how I choose to represent it, whether I use some coordinate system that I make up, or whether it's a camera coordinate system that we use in WebGL, or it's some other coordinate system, that part is arbitrary, but the basic results in geometry are independent. So if you think back, if you studied it from a Euclidean point of view, and you try to say, well, when are two triangles congruent or identical, you develop theorems like side angle side. If two sides are the same and the angle between them are the same, then the two triangles are identical. See, that says nothing about any representation in a particular coordinate system. So that's the path that we're going to follow, at least for today. Okay, now what about scalars? They're the thing we start with. They're not really a geometric entity in the sense that they don't have a geometric property that you could measure a length or a width or a volume or anything like that. They're basically, in real life we'll use, or in computer graphics we'll basically use the numbers. But if you want to abstract that a bit, you can say they're members of sets. So a scalar x, say, is a member of a set, and it obeys certain rules. That these are discussed a lot in the appendix to the book, that you have two operations, addition and multiplication, and they obey some fundamental rules like associativity, commutativity, and each element has an inverse. So every element has an additional inverse. So if x there's an element y, such that when you sum them together you get the zero element, which is called the additive the additive zero, and likewise there's a multiplicative identity. So if you have x, there's an element y, such that when you multiply them together you get the multiplicative identity, which we call 1. So in the number system, those correspond, the identities are 0 and 1, and we know things like a plus b is the same as b plus a, and a plus b plus c is defined no matter what order we do the additions in. We can add a plus b first, or we can add b plus c first, and we get the same result. Commutativity, that if I multiply a and b together, it's the same as multiplying b times a. So that's true for scalars, and the obvious ones that satisfy that are real numbers, complex numbers that we'll use a little bit later when we talk about things like fractals. But other things satisfy it. Rational functions, the ratio of two polynomials satisfy all of these rules. But let's, for now, we can assume that scalars are and the real numbers will be the same. Now vectors we are going to define from a physics point of view, and we'll see the difference a little bit later, probably in the next lecture, when we talk about how mathematically or in engineering what you call a vector is a little bit different from what a physicist might call a vector. But from a physical point of view, a vector is any quantity that has both a direction and a magnitude. So we understand things like velocity. You go at a certain speed, which is the magnitude, and you go in a certain direction, and when you combine those together, you get velocity. Forces or other things. You have a force which has a magnitude, but it also is in a certain direction. Now, the most important one that we're worried about, and obeys exactly the same definition, is a directed line segment. So a line segment is a piece of a line. A line is an infinite thing in both directions. A line segment is just a piece of it between 2 points. Directed means that we can talk about the line segment starting at point P and going to point Q, and we'll call that V or something. I'll use lowercase letters generally for vectors, and they obey the same rules. Obviously, the magnitude of that is its length, and it obviously has a direction that it's pointing in. Now, what kind of operations make sense with vectors? And there are two that define what's called a linear vector space. One is that we can talk about vector addition. So if I add two vectors together, I get a third vector, and so what we see over here is vectors u and w, and they're being added together. Usually we call this the tail to head rule, the head to tail rule. We connect the first one from the tail of the, let's see, here's the tail of the first one. We connect it to the head of it to the tail of the second one, and now the new vector connects the tail of the first to the head of the second. Now notice the most important thing actually about vectors is that they have no position, and this is very important. Some textbooks like to call them free vectors, but but we're going to say mathematically as a vector is something that has magnitude and direction, but it doesn't have a position. You can move these around and they're point in the same direction and they have the same length, and so they're the same vector. Now vectors also have a zero vector. That's the vector that has no magnitude, and if it has no magnitude, then the direction makes no sense. So it has an undefined direction or orientation. The two vectors, for every vector, let's put it this way, for every vector, there's a vector that when I add them together, I get the zero vector, and if you look at this graphically, it's obviously the vector that has the same length but points in the opposite direction. We also have another operation which says that I can scale the length of the vector. So if I multiply it by a positive constant, it gets longer or shorter, but points in the same direction. So it's only changing the magnitude. If this constant, see this is alpha represents a scalar. If this alpha is negative, then you can make it longer or shorter, but it points in the opposite direction. So if you want to formalize that a little bit, the formalization of that is what's called a linear vector space, and it defines these two operations we've talked about. That's all you need is the multiplication of a vector by a scalar, which gives you another vector which has its length shortened or elongated, and if it's negative, as we said, points in the other direction. And we have vector-vector addition, which obeys rules like u plus v is the same as v plus u. Okay, so you can write expressions like this, and you say, well, why does that make sense? Well, it makes sense because what you're doing is you're multiplying the vectors by constants. So 2 times w is a vector. Minus 3 times r is a vector. We add the vector plus vector, we get a vector. U plus a vector is a vector. So this is a valid operation. Now again, the point is that these are all the same because vectors don't have any position. So these three vectors all have the same length. They all point in the same direction, and they're identical. Now that's a problem because we don't want to. We deal with things that have a location somewhere, and the thing is that what results is that a linear vector space, even though it has vectors and scalars in it, isn't sufficient for doing the kind of things we want. So we need to add a point, and a point is different from a vector. So a point is simply a location in space, and operations, there is one important operation between a point and a vector. Now you can look at this two ways. You can say it's point vector addition or point subtraction, which are exactly the same thing. But let's define it this way. Suppose I have 2 points, which are 2 locations in space. Then I could say there's a directed line segment or a vector going from one to the other, and I could write that mathematically and saying this point P is what I get by starting with the point Q and going in the direction of V for the length of V, and that defines this operation vector point addition. Another way to do that is you can think of it in terms of a subtraction operation, which says looking at P and looking at Q, if I take the difference between P and Q and call that the vector, the operation point subtraction, then that says, oh, if P minus Q is this vector V that goes from P to Q and has the length, which is the distance between Q and P. So points are a different type, they're fixed. And notice a point is an idealized point. It has no property like its size or its length or anything like that. It's simply a location in space. I just have to draw it to have some size. Okay, now that defines a different kind of entity, which is from a linear vector space, which is called an affine space, which is the crucial one for everything we do in graphics. And what it is in terms of a vector space, it's a vector space and we add a single point to it. Well, why does adding a single point really help? Well, the idea is that if you have a single point, then I can get to any other place in this space by adding a properly chosen vector that points in the right direction and has the right length. So adding a single point, which we can think of as an origin, is sufficient to give us all of the points in space that we want. So the mathematical definition is a vector space is a point plus a point gives you an affine space. Now what operations do you have? Well, the vectors are going to satisfy vector-vector addition. They're also going to satisfy vector scalar multiplication. Now point vector addition is the operation that I just had, that you start at a point, you go in the direction of the vector, the length of that vector gives you a new point. So points are generated by point vector addition. And then we have all the scalar operations using multiplication and addition. Now to make this all work kind of nicely, I'm going to define the following two operations. 1 times a point. See, generally, it doesn't make any sense to talk about a scalar times a point, because what does it mean? A point has no length kind of or size kind of property, so multiplying it by a constant doesn't really make any sense. But there are 2 special cases that we're going to use, and we're going to define 1 times a point to simply do nothing to it, and 0 times a point to give you a 0 vector. Okay, and you'll see in a few minutes why that's important to have those 2 cases. Okay, so let's see how far we can get. Now we still don't have a representation. We still haven't said anything about values in the 3 dimensions of x, y, and z. We just said there's these points out there and vectors out there, and they're parts of an affine space. So let's see how far we can get. So let's suppose I have a point and I have a vector pointing in a certain direction, and I consider all the new points I can get for different values of alpha. Let's assume for a second that they're positive. So I start at p0 for alpha equals 0, because this is 0 times d is giving me 0, and I add on a vector of 0. It just leaves that point alone. And any other value of alpha starts pushing me off in the direction of d. And so I get all the points going in this direction, and lo and behold, they form an array. Array is an infinite line in one direction. And it doesn't have the negative values going off to infinity out here, but it has all the values going on forever. So I get a line and if I allow alpha negative, what does negative alpha do? Well, that reverses the direction of d, because it's like multiplying alpha, a positive value times minus d. So I get all of the points along this line, allowing alpha to be both positive and negative. And so we have a nice definition of a line without having any representation. This is known as the parametric form because alpha is a parameter. That for every value of alpha, I get another point along this line, and as we'll see as we go through the course, that parametric representations are the most powerful representations that we can have, and we'll be using them very, very often. Okay, now if I give you a representation, now let me just look at a couple of cases where we say, okay, now let's consider 2 dimensions, and I say, okay, I'm going to have x's and y values. So let's set aside our abstract view for a second and say, well, let's look at points in space, and I want to argue why the parametric form is so important. So if I say, look, here's a line, that's the simplest thing as I could want to deal with. I can define it as y equals mx plus h, where m is the slope of the line and h is the y-intercept. And I say, well, that looks pretty reasonable. Can I define all lines that way? Well, the answer is no, because what happens when you have a line that goes straight up in the y direction? The slope is infinite, so that line doesn't exist. And this is one of the problems when you use representations, and especially when you use explicit form. As I have it here, no matter what d I pick, I'm always going to have a direction that makes sense. It's when I go to this particular representation, y equals mx plus h, I can get into trouble when I have vertical lines. And if I reverse it and say x equals 1 over m times y plus a constant, That doesn't work for horizontal lines, so that's a problem, and it's more than just a little mathematical problem. It's a real problem when you're trying to draw lines as fast as you possibly can, and you say, well, it might work for some, and I'll have to use this other form for others. That's going to slow you down. So that's bad form. Now there's another form called the implicit form, where you look for an equation in 2 dimensions involving x and y that's equal to 0. So the form for that, ax plus by plus c, always describes lines, and I can in fact represent any line that way. See, what will happen is if I have a horizontal line, then A will be 0. If I have a vertical line, B will be 0. So they all fit in here. But in general, this is not quite what you want, because you have to solve this. You have to then look, well, is A 0 or B 0? And if I give you an x, then I'll find a y, and I have to do a solving. And if I try and extend this to something beyond the line, I'm really in trouble. Now, the parametric form is kind of nice. So if I start with this, and I now say, okay, I'm going to impose some coordinate system on this problem and look at it in 2 dimensions, then I could write a separate equation for x and y parametrically and say, okay, if I want a line that goes through x0, y0, it goes through x1, y1, here's a little form of that line and we'll come back to this again, that if alpha equals 1, then you get x0, y0. That's good. If you let alpha be 0, then you get x1, y1, and so it goes through those points, and in fact it's a line in the direction defined by these 2 points. Okay, now let's go back to the abstract form again, and this is something we've already said, that it says, okay, well, array is just values that you get for alpha greater than or equal to 0, so it just goes off in one direction. Now you equivalently could say, this is point vector addition. Now if I use the notion of point subtraction to define this vector, because every vector could be defined by the subtraction of 2 points, I could say there exist 2 points that correspond to having this length of v and the direction of v, and let's call them r and q. And so if I substitute r minus q for the vector v, I can write it in this form, just algebraically working this out. So this looks like alpha r plus 1 minus alpha q. And what will happen is for alphas between 0 and 1, I get all the points between q and r. And for alpha bigger than 1, I get the points out here. For negative alphas, I go down in this direction. So it's just another form for doing that, but it's actually a very powerful form that's tied to the notion of convexity. Now, convexity is going to come up over and over again, and it applies in any number of dimensions. Here it's drawn in 2 dimensions, and the rule is this, that if I draw a line segment between any 2 points in or on the object, okay, now that makes sense without any kind of representation, because we just saw that we could always define a line given 2 points on it, and the definition is that an object is convex if and only if all of the points lying on that line connecting them, on that line segment connecting P and Q, lie inside of the object. So here's a convex object. Any place you put P and Q, the entire line segment will be inside. Here's a non-convex object here, where if you pick P here and you pick Q here, obviously it comes outside of the island. And that's the notion that's really embedded back over here when I first started talking about this form. This is a very powerful form for representing lines, because you, by just saying, oh, if I only consider the points between 0 and 1, I'm talking about the segment that goes between Q and R, and that's exactly what we're talking about here with P and Q. Now, I could extend that notion a little bit and say, what about if I have a lot of points and I look at what's called an affine sum? Now, this is a little tricky. I'll have a picture on the next slide of what we're getting at here. Is suppose I just write down P equals alpha 1 P1 plus alpha 2 P2. You could say, hey, that doesn't make any sense. Why doesn't it make any sense? Well, there's no operation for a scalar times a point. So what are you talking about here? Well, I can do some algebraic manipulations here and say that this makes sense if the sum of alphas equals 1. And I show that in the text. And if that's true, then this is called an affine sum. So P equals alpha 1 plus all the alpha i's, pi's up to alpha n pn for a set of n points is called the affine sum if this is true. Now I'm going to put the additional restriction on that alpha is greater than or equal to 0. Notice that also implies that alpha has to be less than 1, because if any of them get bigger than 1, then somebody else is going to have to be 0 because of this sum. That defines what's called the convex hull of the objects, which will come into effect later in the course when we talk about curves and surfaces. But it's what you get by what's called shrink wrapping. Think of it this way. Suppose I have a collection of points, and this is a notion, again, that applies to any dimension. This holds in 3 dimensions, 2 dimensions. In two dimensions, which is easier to see here, is I give you a collection of points. And suppose I have a giant rubber band, and I put it around here, and that rubber band now squeezes shut. What it's going to do is stop at this point, and be stretched like a line over here and a line over here, connecting all these outer points. And that's like the same as if you think of a surface and you took a big piece of saran wrap and you wrapped it around it. It shrink wraps everything that's in there. And if you think about the extension of this idea, what you get is something that has a bunch of flat polygons connecting these outer points. And this is called the convex hull. Another way to see why it has a notion of convexity, notice on these outer surfaces, this includes all of the points going from this one to this one here. It includes all of the points going from here to here, and so on. In fact, it includes all the points going between any pairs, and then you could extend that to any any 3s and 4s and so on. And I think you can convince yourself of this. And this is going to be very important later. Okay, now curves. We want to go from talking about curves that we can easily draw in the plane, like the line segment, to looking at things like surfaces. And the surfaces are really much more important in 3-dimensional computer graphics. And what I want to argue is that if you have a parametric form, for things much more complicated than lines, you'll get a curve if you just have one parameter and you vary it in some way. This might be some polynomial curve over here. But if you have 2 parameters, you get a surface. And we're going to now use that notion to talk about things in particular like planes. So here's an idea of how we can get a plane, and then we'll build up to a triangle in the next slide. So suppose I give you a point and 2 directions. Okay, that's going to define a triangle, and a triangle lives in a plane, so it's equivalent to defining a plane. So here's how it works. Suppose you have a fixed point over here, and you have vector u and a vector v, that I can now talk about drawing a third vector from the head of the first u to the head of v, and so the tail of this new vector is at the end of u, and its head is at the end of v. So it's like the vector sum. And if I now start considering all of the points alpha u plus bv r, I in fact have defined a plane. Now notice again why this makes sense. Beta times v is a vector, so alpha times u is a vector, vector plus vector is a vector, and a vector plus a point gives me another point. So here's a 2-parameter family, and it's going to define all of the points not only inside of this triangle that I just drew, but also lots of points outside. Now I can also equivalently just look at this and say, well, why don't you call this a point and call this a point, and maybe this is maybe a little more familiar because it says, okay, that 3 points define a triangle. but I could define u and v by just taking p minus q and q minus r and putting them into this formula. So these are equivalent ways of just saying that a plane is defined by a point and two vectors or by 3 points. And as you can see, defining a plane is essentially the same as defining a triangle, or maybe a little better statement is that every triangle defines the plane in which it exists. Okay. Now let's go back and look at triangles in a slightly different way. Suppose I have those 3 points, and now I want to say, well, how do you describe the points that are inside of it? That gets a little bit trickier. It's not clear from this formulation here that I can say something as simple as, oh, let alpha be between 0 and 1 and beta be between 0 and 1. That's going to give me the inside. Have to be a little bit more careful with that. So let's do the following. Let's use our notion of lines to build up every point that's inside of a triangle. So let's start with P and Q, and I start looking at the convex sum of P and Q. So I can look at alpha P plus 1 minus alpha Q, and that's going to define all of the points along this line segment going from P to Q. Now suppose I take an arbitrary point here for some value of alpha between 0 and 1, and now I connect that point with R. Okay, so I'm going to connect it by R. How? I'm going to draw this line. I'm going to use a new parameter, beta, that says every point along this line, we'll call T, is of the form beta times S plus 1 minus beta times R. Okay, and I can reverse that. Obviously, I could say 1 minus beta S plus beta times S times 1 minus beta R, or I can do beta R plus 1 minus beta S. That doesn't matter at all, just which direction I go. But the important point here is that using this argument, what I've said, what I can conclude is that for alpha and beta between 0 and 1, I get every point inside this triangle, and I never get any point outside. Because if I draw this line, close to P connecting R, I get all of these points over here, start over here, I get all the points over here. And so it's going to fill the inside. And it sort of is a convincing argument of why surfaces, which is what I'm getting here, are 2-parameter families of curves. They become surfaces. Okay, this notion of defining triangles this way, and it's really important for computer graphics because triangles are what we almost always want to deal with, are called the barycentric coordinates of the triangle. And we can do it in a number of ways. One way is if you add it all up, I'll let you either read the book or fool around for yourself. You can take this form and manipulate it algebraically and put it into an equivalent form that looks like this: alpha 1 P plus alpha 2 Q plus alpha 3 R. Hey, that's looking like the convex sum I was talking about a couple of slides ago, which only makes sense if alpha 1 plus alpha 2 plus alpha 3 equals 1, and the alphas are greater than or equal to 0, which also forces them to be less than 1, less than or equal to 1. And this is called the barycentric coordinate representation of a point, but also it's the barycentric coordinate representation of a triangle where alpha 1, alpha 2, and alpha 3 are essentially the coordinates of any point within that triangle. And again, we're still without a particular representation. We've gone pretty far without having to rely on the notion of a coordinate system. Okay, one more concept I want to introduce today. And this only really makes sense if you're talking about really a 3-dimensional space. Not everything I've said up until now works in an n-dimensional space. You can talk about the idea of a plane in an n-dimensional space. That's a little bit different. You can talk about what would a triangle be in an n-dimensional space. But this idea of a normal, I think, really is going to make much more sense if we restrict ourselves to 3-dimensional spaces. So we say, suppose I have a plane, and we've just talked about how you define a plane. Well, a plane can be defined, let's look at where it says, okay, I give you 2 vectors and a point, and that defines a plane, and if I give you 3 points, I can always give you the vectors u and v. Now, the important point here is that in 3 dimensions, what I can do is use the cross product. And I think you should all remember the cross product from math and physics or somewhere in high school. It just says that there's a way of combining u and v such that you always get a third direction which is orthogonal or normal to both u and v. Well, since u and v define the plane, this normal is normal to every point in the plane, and it's obviously called the normal to the plane. If you write that down mathematically, it says that any point in this plane, which can be represented by some alpha and some beta, as we had a couple of slides ago, minus p is a vector in the plane. It's orthogonal to this, to the normal to the plane, and we had something else in 3D called the dot product. Actually, the dot product exists in any number of dimensions, and the dot product is always 0 when two things are orthogonal. So here's an alternate representation of a plane, or it'll be an alternate representation of a triangle if we define this by 3 points, and we'll come back and see this later. Okay, so in the next lecture, we can get to perhaps the more familiar way of looking at things through their representation, where we introduce the notion of a coordinate system for vectors and a frame for when we're considering an affine space where we have points plus vectors.